Let's just dive right in, shall we? Welcome to this explainer where we're going to unpack what is honestly the most powerful tool in all of mathematics. I'm talking about algebra. Now look, I know exactly what some of you are thinking. The second letters start getting mixed up with numbers, it can feel a bit like staring at a really intimidating bowl of alphabet soup. But let's completely reframe that today. Algebra isn't here to trip you up or confuse you. It's actually designed to empower you. Think of it as this sleek, universal shorthand that takes messy, complicated real-world problems and just distills them down into simple, elegant formulas. By the end of this explainer, I promise you're going to see those letters not as roadblocks, but as the ultimate mathematical shortcut.
So to get us there, we've got a pretty clear roadmap today. First, we'll look at using letters for unknowns. Second, we'll cover the basic rules of algebra. Third, we'll dive into number substitution. Fourth, we'll handle some harder numbers. And finally, we'll see it all come together with real-world formulas.
All right, moving right into section 1, letters for unknowns. Why do we even use letters in the first place?
Well, imagine you've got a job that pays by the hour. If your hours and your pay rate are constantly changing, writing out a brand new, specific calculation for every single scenario is incredibly tedious. We need a simpler way to handle information that fluctuates, right? Now take a look at the left side here. We've got this clunky word formula. Amount earned equals hours worked multiplied by pay rate. That takes forever to write out. But if we let the number of hours worked be N, the pay rate be P, and the total weekly wage be W, that whole bulky sentence just collapses into one elegant equation. W equals N times P. It's brilliant and it works for literally any job.
Let's actually put this formula to the test using an example straight from the Cambridge curriculum. We need to find the weekly wage when N equals 40 and P equals 5. In plain English, that just means someone worked 40 hours at a rate of $5 an hour. By substituting those numbers into our new algebraic shorthand, we get W equals 40 times 5, which instantly gives us a total weekly wage of $200. See what we did there? We took a real-world concept, represented it with letters, and then just swapped those letters back out for specific numbers to grab our answer. Simple as that.
Okay, on to section 2, the rules of algebra. Think of this as learning the grammar.
Because really, algebra is basically a new language. And just like English or Spanish, it has specific grammar rules to keep things super streamlined. First off, we drop the multiplication sign entirely. Let's be real, it looks way too much like the letter X anyway, which just gets confusing. So 4 multiplied by t is simply written as 4t. Second rule, when you multiply a number and a letter, the number always goes in front. So p times 6 becomes 6p. Third, we like to organize our formulas nicely by starting with the single letter we're trying to find. Like if we want to find perimeter, we write p equals 2l plus 2w, keeping that p right there on the left as the subject. And finally, we totally ditch the traditional division symbol. In algebra, division is almost always written as a fraction. Sticking to these rules literally transforms messy arithmetic into clean, readable expressions.
Which brings us to section 3, basic number substitution. This is where you make your move.
So, to actually use our universal shorthand, we have to substitute our letters with actual numbers. But here's the catch. This only works if we follow a very strict protocol, the order of operations. You absolutely cannot just plug numbers into an expression and read it left to right like a novel. Doesn't work that way. First, you've got to handle any brackets and indices, your powers like squared or cubed numbers. After that, you tackle any division and multiplication. And only then, at the very end of the process, do you do your addition and subtraction. If you mess with this hierarchy, the entire formula just completely falls apart.
Let's walk through the logic step by step so you can see what I mean. We've got an expression here, 4x plus 3, and we need to find its value when x equals 2. Step 1. We substitute. We swap out that x for a 2. Now remembering our grammar rules, 4x means 4 times x, so our expression becomes 4 times 2 plus 3. Step 2. We check our order of operations. We've got a multiplication and an addition. Multiplication always wins. So we do 4 times 2, which gives us 8. Step 3. Now we finish up with the addition. 8 plus 3 equals 11. By strictly following the sequence, we just effortlessly arrived at the right answer.
Now pause for a second because I have to explicitly call out a massive pitfall here, one that catches countless students completely off guard. When you see an expression like 3x squared, what exactly is being squared? The rule is incredibly clear. 3x squared means 3 multiplied by x multiplied by x. Listen closely. Only the letter x gets squared. The 3 does not. It definitely does not mean 3 times x times 3 times x. So if x is 3, the formula becomes 3 times 3 squared. According to our trusty order of operations, we calculate that index first, so 3 squared is 9, and then we multiply it by the 3 sitting out front, which gives us 27. Seriously, do not fall into the trap of multiplying first and then squaring the whole thing. It's a classic mistake.
All right, moving into Section 4, handling harder numbers. It's time to level up.
Because let's face it, the real world isn't just neat, positive whole numbers like x equals 2. If you look at the exercises here, you'll see formulas demanding substitution with messier values, like decimals, say a equals 2.6, or fractions like a equals 4 over 5. But here's the beautiful part. You don't need to learn a single new method for this. The exact same algebraic scaffolding and order of operations apply. Yes, the arithmetic itself requires a bit more careful calculation, but the overall process is identical. You substitute, you follow the order of operations, and you solve. Same as always.
We do need to take special care when negative numbers crash the party, though. Let's look at this one. We need to find the value of 2x squared plus 6 when x equals negative 2. When we substitute that negative 2 into the squared term, remember your basics. A negative times a negative becomes a positive. So negative 2 squared becomes a positive 4. Then we take that positive 4 and multiply it by the 2 out front, getting 8. Finally, we add the 6 and boom, we get 14. Just remember, if you aren't paying close attention to those negative signs, your entire calculation is going to unravel pretty fast.
And finally, Section 5, Real-World Formulas. This is algebra in action.
So you might be wondering why go through all this trouble. Well, because these exact tools are what scientists, engineers, and architects use every single day to map out the physical realities of our world. For instance, imagine dropping a pebble off a tall cliff. How do you calculate the exact distance it's fallen after a specific number of seconds? You obviously can't just guess. You need a formula that accounts for the constant acceleration of gravity, and you need those algebraic substitution skills we just perfected to actually solve it.
Luckily, we have that exact tool right here. The formula is s equals 1/2 gt squared. If gravity, g, is 10, and our time, t, is 12 seconds, we literally just substitute those values right in. We square the 12 to get 144, multiply that by 10 to get 1440, and then divide by 2, which gives us exactly 720 meters. It's like magic, but it's just math. And algebra unlocks all sorts of other real-world applications too, like the ones shown here, whether that's calculating the surface area of a cuboid, the elastic energy of a string, or even figuring out the focal length of a camera lens.
So the very next time you see a formula packed full of letters, I want you to remember that it is not some evil puzzle designed to frustrate you. It's actually a highly efficient, incredibly potent, universal shorthand. Whether you're calculating weekly wages, measuring the surface area of a building, or tracking the physics of a falling object, you now know the grammar. You know the order of operations, and you know exactly how to substitute. The only question left is, what real-world system will you decode next using the universal shorthand of algebra? Thanks so much for joining me for this explainer, and keep exploring the math that shapes our universe.